All right. Hi, everyone. My name is Saf Mueller. I'm a software engineer in the cloud networking group. I'm working on OpenStack Neutron, upstream, contributing patches, so on. And I'm here to talk to you about Neutron. This will be an introduction to Neutron. It's a very introduction level talk, kind of a broad overview of the concepts of Neutron, why do we need it, and so on. And if you would, we're gonna have questions, but we're gonna have them at the end. I would love to answer any questions, and also after the talk, I'll still be here on the chat channels, email, and so on. All right, so I suppose we'll begin. I'm at slide 2. So normally you kind of start with a giant graph and you kind of do an overview of the components and so on. I wanted to start out with the why. So I narrowed down 3 main objectives of Neutron. The first one would be just providing connectivity for your VMs. Your VMs should be able to talk to one another and have preferably internet connectivity. The second object is basically isolation. You really wouldn't want your tenants to be able to see or talk to one another. If you're using a public cloud use case, your tenants should be absolutely isolated. The second thing is kind of more conceptual or abstract. That's the idea of networking virtualization. So the tenant, via self-service, can create his own network, his own routers, and I actually will expand on that in a minute. And the third thing would be stuff as a service, right? We affectionately call it crap as a service in our team. We'd be referring to load balancing as a service, firewalls, and VPNs at this time, and there's more stuff coming in future releases. So let's talk about networking virtualization. We are at slide 3. Sorry. So this is kind of a use case or an example of networking virtualization. So you've got a new tenant on your cloud. It could be a public cloud, a private cloud, whatever. And he wants to basically create bring up an application, right? In this case, for example, some WordPress application. So he would create his own network, and this is, of course, via self-service, so no administration intervention. So just the user or the tenant itself creating his own network, hooking up this new private network to the internet, creating a new database instance and 3 additional web servers with WordPress already installed. Then he can make sure that the database is accessible exclusively by the web servers, right? We wouldn't want any other access to the database instance. He can create his own load balancer via load balancing as a service. The load balancer would be pointed at the web service. He could attach a floating IP, which would be a real internet routable IP, so an IP that's actually exposed to the internet, and point it at the load balancer. And then also additionally make sure that the only viable or allowed traffic would be incoming HTTP traffic, right? We'd probably want to filter out any other types of traffic. So the networking virtualization is implemented here. Basically the idea that you can just create your own network, and this new network is completely logical in software, and it's an entire new broadcast domain. So VMs in other networks by default can't see your traffic. So you're just creating your new virtual networks. And you can do this via the different methods, right? The CLI, the API, the GUI. Of course, another newer client of Neutron would be Heat. So this would be a perfect use case for platform as a service. Of course, this is kind of exterior to Neutron, but it's also another interesting use case. So next slide. So we talked briefly about the why or the different use cases. Let's talk about, kind of do a top-down approach and kind of start deep diving into Neutron. So the core resources or the core concepts of Neutron would of course be ports, networks, and subnets. And we can see the relation here. So before we kind of dive into the relations, what's a port? A port would be basically the representation of how a VM would be connected to a network. So a port would hold the IP and MAC addresses, and of course, what network is this port connected to? A network would be basically a broadcast domain. If you're not familiar with the term, the idea is that if you send out a broadcast, which is a message that's supposed to reach everyone else on your network, and that's exactly the definition of a broadcast domain, right? Basically, who else receives a broadcast that you send? And then you've got a subnet. So a subnet is basically an IP range. Normally you would have a single subnet connected to a network. In the real world, you can also, you can basically create as many subnets as you'd like and use the same physical network. So we allow that in Neutron as well. And you can see the relations here. Basically, you can have many ports connected to a single network, and then again many subnets connected to that same network. In this specific example, the first two ports are connected to the VLAN 10 network, and you can see that they belong to the first subnet, and the third port would be connected to the second subnet. All right. Next slide. So we talked about a network briefly. It turns out there's different types of networks. I guess the first and simplest type of network would be an external network. An external network is a real network that's reachable or routable from the internet. We model external networks in Neutron via something called a provider network. A provider network has two main use cases. We'll talk about that in a second. Provider networks can be created by administrators. And the idea is that a provider network is basically mapped to an existing network that's already on your data center, right? So, for example, if you're implementing your networking with VLAN, and for example, you've already got a real network on your real data center that's using VLAN 20, then you can just create a new provider network in Neutron and have it use VLAN 20. So it's mapped to an already existing network on your data center. It has two main use cases. You would basically model an external network via a provider network. Also, if you're not as interested in the idea of a tenant network, which we'll talk about in a second, you can just connect VMs directly to provider networks. That's kind of a more traditional networking topology, but we won't be talking about that. The third kind of network is a tenant network. A tenant network is something that a tenant can create on its own, right? This is a self-provisioned networking. This relates back to the idea of networking virtualization. A tenant network is isolated from other tenant networks, right? And then you can use something called a router, which we'll talk about in a second, a virtual router, to basically hook up your tenant networks to one another or to the internet. Next slide. I want to talk about the idea, I basically emphasize the idea of the different network types and then kind of see how this relates to IP addresses and routing. So a tenant can create his own network, and then he, in this example, he created his own subnet, the 10.0.0.0/8 subnet. And the range of this network would basically be between all of the compute nodes, right? These compute nodes are the machines that are running your virtual machines. And your virtual machines would basically be getting IP addresses in the range of the tenant network that you just created. We're using different ideas here, like a DHCP agent, but we'll talk about that later. Then there's this idea of a network node, right? So why do we need this network node? Basically, the VMs are in an internal network, right? The 10.0.0.0 network is just a network that you just arbitrarily created on your own. You can't ping something on the internet right now. Why? For example, your physical router on the top right on this topology doesn't know where 10.0.0.0 is, right? It doesn't know about that network. So in Neutron, we have this idea of a network node. So a network node is where we basically create virtual routers, virtual Neutron routers. So in this example, the user created his own tenant network, and then he created his own virtual router. Again, a tenant can self-provision virtual routers. Routers are physically located on your network node and are managed by a component called the layer 3 agent, which we will talk about in a minute. So in this example, the user created his own router and then hooked it up to two networks: the tenant network, which he also created, and also connected this virtual router to the provider network, which was actually created beforehand by the administrator, not by the tenant. So here we can see that the virtual router, if we just ignore the floating IP, okay, you can see the floating IP is the third row, and we haven't talked about that yet, but let's just focus on the first two rows first. So the virtual router is connected to two different networks, which is something that the user chose to do. So it has an address on the internal network as well as an address on the external network. And at this point, the VMs can actually ping redhat.com or write any address on the internet. So here, of course, to do that, we'd have to implement NAT, or network address translation, right? The VMs are, for example, pinging redhat.com. That request reaches the virtual router on the network node. And basically, the virtual router has to change the source IP address from an address on the tenant network to an address on the provider network. So basically, the request would have a source IP address of 212 and so on. Basically, an address on the external network would reach redhat.com, come back, and then the network node or the virtual router would basically perform the reverse operation, right, and forward the traffic to the correct virtual machine. This use case covers VMs connecting outside, basically traffic that's originating from inside of a VM to the outside. This, I guess, would be more. This use case would be more interesting in private clouds and data centers, on-premises data centers, where maybe you'd want to do something like VDI, or basically provision VMs for your end users. Oftentimes, you also provision VMs to be used by services or servers. Like just earlier, we talked about bringing up a VM and using it as a WordPress website. In this case, you'd really want your VM to be accessible from outside of your cloud, right? Without floating IPs, this wouldn't be possible. Your VMs would not be able to be accessed by outside of your cloud because, if I'm at home, I can't ping 10.0.0.0.1. This address is behind a NAT. So here comes the idea of a floating IP. I would be able to allocate a floating IP from the range of this provider network, and then basically attach the floating IP to a specific VM. For example, the first VM on the left, the 10.0.0.0.1. In this case, any traffic that's coming in to the floating IP would hit the virtual router, which has this configuration, and knows that whenever any traffic reaches that floating IP, it knows to forward it to the correct VM. So this is kind of an overview of how the different networking types are used, NAT and floating IPs. Next slide. So I started this talk by talking about graphs and an overview of components. So here it is. So there's a lot of information on this slide. Specifically, I'm talking about the 4 different networking types, right? There's the management network, the VM network, the internet, and the API network. This would be the ideal case, right? If you look at the upstream documentation on OpenStack.org, they have something very similar, where you actually separate out into 4 different networks. Again, this would be the ideal state. Of course, here you can see that I separated out the API network and the internet network to 2 different physical networks. You could do that. You could also just use 2 different VLANs. That's also a very strong idea. But basically, let's talk about these different networks, right? No matter how you implemented them, but what's the idea? What's the role? So actually, we'll just start with the management or the orange network and the VM data network. So Neutron is divided into all of these different components, right? There's the Neutron service itself. Then there's all of these agents. There's the layer 2 agent and the virtual routers, the DHCP agent, the metadata agent. So all of these different components talk via the management network. They talk via a mechanism called RPC, mostly AMQP. You could use Cupid or RabbitMQ. Whichever way, these different components we would be normally talking through some sort of messaging implementation. And you'd really want to separate that sort of traffic to a different network. So all of that traffic would be flowing through the management.
Asaf, we've lost audio, I think. Yeah, a number of people are saying the same. Can you just mute and unmute your line on Intercall?
Yeah.
There we go. It's back now.
Thank you.
Yeah, I can hear you now. Yeah, that's fine now. I'll say if it does it again, but just it does it again, just mute and unmute again. That should be okay. Thanks.
All right. So okay. So I don't really know when people lost me, but so we were talking about the management network and the VM network. The VM network would basically be where all of the actual traffic of the VMs themselves would be flowing, right? If a VM on this compute node would want to talk to a VM on this compute node, you'd want to separate that kind of traffic from management traffic. So you've got finally two additional networks, the API network and the internet or the external network. Both of these networks have to be accessible from the internet. For example, if we're talking about the public cloud, and in my home, I'm trying to make these API calls. For example, create a new VM, create a new network, and so on. So I would want to use the API network. And this node here on the top left, the API services node, would be...
Question?
Sorry?
May I ask a question?
We'll do questions at the end, so just try to...
okay.
Yeah. So you've got four different nodes here, right? You've got these compute nodes, which we talked about earlier, running the virtual machine. You've got the network node, which we also talked about. The API services node would just be running all of the different OpenStack servers. For example, the Nova server, the Ceilometer server, in this case, the Neutron server as well. In the ROS deployment installer, you would normally install the Neutron service itself along with all of the other API services on this top left node and not on the network node. So you would need this API services node to be reachable via the API network from the internet. And it would be actually receiving API calls, for example, create a new network. The internet network, the one that's in the black color, that would be basically the equivalent of the VM data network just for external traffic, right? Next slide. So I want to start talking about the different components. Here again, we have four different nodes, the API node, the network node, and a couple of compute nodes. The Neutron-related agents and services are in bold. And as I said earlier, the API node would be running all of the different API OpenStack servers, Neutron amongst them. Normally, I'd guess you would install your database on a separate, dedicated node as well as your messaging broker. That's besides the point. So I guess we'd start with the Neutron service itself. The Neutron service itself here in the top left would be located on the API node, and it's basically receiving different API calls, create network, delete network, create router, delete router, and so on. Persists that data in the database, right? And then using the messaging broker, it basically forwards or sends out notifications to the different agents residing in different machines. So, for example, if the Neutron service just got a create router API call, it would persist that data in its database. Then using this type of messaging, basically forward a notification to the layer 3 agent on the network node, which would do the actual work. So let's talk about the agents. First, let's talk about the layer 3 agent. The layer 3 agent receives notifications from the Neutron service and then locally manages running virtual routers on the network node itself. So it would be receiving a create router notification, then actually creating a router via a dedicated routing table on the machine itself. The DHCP agent would be in charge of IP address allocation. So it receives create network, delete network, and so on notifications from the Neutron service, then uses a Linux technology called DNS mask. DNS mask, in this case, would be used basically as a DHCP server, so that later on, when VMs are booted, they can send DHCP requests via the VM data network, right? Here we have a view of the orange, or the management network. But when a VM is booted, it sends out the DHCP request via the blue, or the VM data network, and that request would be received by the network node by the DNS mask instance, or the DHCP server instance of that specific network, which would be able to reply. So last but not least is the layer 2 agent. The layer 2 agent would normally be installed on the network node, as well as all of the compute nodes. The layer 2 agent basically provides connectivity, so it would have to be connected to both the management and the VM data networks. And it has many use cases. For example, when a VM is brought up, and we will be talking about this use case more in depth later on, basically when a VM is created by the Nova service, it's normally created, for example, with a single virtual NIC, which would be connected to some specific network. The layer 2 agent would receive this kind of notification and do the actual networking connectivity. So it would make sure that that VM is actually connected to the correct network and not, for example, other networks. The metadata agent is not as interesting, not as critical to our understanding of what is Neutron, so I'll just be skipping that. Next slide has well, basically more of the same. We've already discussed this. Next slide. So here, this would be more complicated than what we've discussed earlier, but this is basically an overview of the interactions between Nova and Neutron. So here we'll be talking about what actually happens when you create a new VM, how do Nova and Neutron interact, and with this would be kind of more important than understanding specifically how Nova and Neutron interact. This would be a great overview of the role of the different agents, which we just talked about earlier. So the first things first, the Nova service would receive an API call to create a new VM. And with this API call, you would specify to which network you would want to hook up this VM to. Next slide, we see that the second stage is basically internal calls between different Nova API services, right? Between a service called Nova API and another service called Nova Conductor. Next slide, Nova basically schedules the VM. It needs to decide on which compute node it wants to run this VM according to available resources. Next slide, it would basically send an RPC or a messaging notification from Nova Conductor to the scheduled Nova Compute agent, right? If in this case the scheduling logic selected the leftmost Nova Compute, or the leftmost host, then it would notify that host that it needs to create a new VM. Next slide. Then we've got steps 5 and 6. So I want to talk about step 6 first. At this stage, the local software on the Nova Compute agent, in this case libvirt, would create a tap device. So what's a tap device? A tap device is basically our way in the Linux world of representing the virtual machine, the virtual NIC of the virtual machine. It would basically be the other end of the cable, right? You've got two ends of the cable. The first end would be basically the virtual NIC of the VM itself. And the second end of the cable, we can just connect to whatever we want. So we can connect that other end of the cable to whatever network. Here we'd really want to connect the tap device to network X, right? And not any other network, because the user wanted to connect the VM to network X. So first off, the tap device is created. Here, we still didn't actually do anything with the new tap device, but it exists. Then Nova Compute sends out an API call to create a new Neutron port. Neutron needs to know about this new VM, right? And it needs to create a port and connect it to network X. So Nova Compute sent out an API to the Neutron service. Next slide. Step 7, Neutron creates the port, allocates a MAC address, allocates an IP address, persists this in the database. The next slide, steps 8 and 9, notifies both the DHCP agent and the layer 2 agent on the specific compute node. So why do we need to notify the DHCP agent? Well, what happens now is basically the DHCP agent receives the notification, the IP address, the MAC address, and the network ID that the port resides on. Then it updates the leases file in the specific DNS mask instance. So the DHCP agent has basically a file with the IP and MAC addresses of a network. This is, of course, so that when the VM sends out the DHCP request later on, he'll properly get an answer. Step 9 would be notifying the layer 2 agent, again via the messaging broker. Layer 2 agent would receive this information. Next slide, step 10. This is kind of inefficiency of Neutron, but basically it would request additional information from the Neutron service. Next slide, steps 11 and 12. This is actually when the layer 2 agent does some actual work, basically configures a VLAN on the local machine, as well as open vSwitch flows. We won't dive further into this, but basically it makes sure that the tap device that was created earlier is connected properly to the right network. It then, in step 12, this is a new addition during the iSouth development cycle, the layer 2 agent now notifies the Neutron service that the port was successfully created and was successfully hooked up to the right network. Next slide, step 13, the Neutron service forwards this notification to Nova. And then next slide, step 14, Nova then sends this notification back to the compute node. Finally, step 15, Nova Compute on the compute node now has received this notification that the port is ready and can now boot the VM. If you spot any inefficiencies here, that's understandable. Next slide. So everything that we talked about until now was specific to the open source plugin, meaning that Neutron is basically pluggable. So you could have many plugins implementing the API being, in this specific example, we had create port. So you can choose an API, and each API implements you can choose the plugin, and each plugin implements the API very differently. So we have many plugins. You've got the ML2 plugin, which is the open source plugin that, internally in the team, we do most of our work on. Then you've got proprietary vendor plugins. You've got the Nicira plugin, Mellanox, Midonet, and so on. Some of these plugins are certified, so that if we can somehow prove that the error or bug is somehow related to the specific vendor plugin, we can just forward the ticket to be handled by the third-party vendor. And it's important to understand that basically the plugin can implement the API whichever way, right? The plugin receives a create port API call. Some plugins are basically nothing more than proxies. They basically take the create API call and just forward it to some third-party server, and that server actually creates the port and does whatever needs to be done. Earlier we talked about these services. So as it turns out, core plugin, you have to choose, right? Just now we talked about the idea of a core plugin which implements the core API, such as ports, networks, and subnets. You have to choose a specific core plugin. In this next slide, the service plugin slide, we see that we have additional services that implement additional API extensions, such as firewalls, VPNs, and load balancers. These service plugins also have multiple implementations. For example, the load balancer as a service, the default implementation would be HA proxy, which is basically a software in Linux which can provide load balancing. You've got other drivers to provide different types of implementation to the same API. So let's just talk very briefly about each type of as a service. You've got firewall as a service. You can basically filter traffic at the network level at some centralized location. So you can decide for incoming traffic into your network, you can decide if you want to allow HTTP traffic, if you want to disallow pings, and so on. You've got VPN as a service. If you like to extend your Neutron network off-premise, for example, if you have some other data center that you want to basically hook up to the same network and be exposed to the same, basically be connected to the same network, you can use VPN as a service. So on the OpenStack end or on the Neutron end, you would basically just hit create VPN and configure it. On your end, off-premise, you would still have to, of course, configure VPN on your own in some manner. Load balancing as a service is extremely popular. It was also the first service plugin. It's if you go to public cloud websites such as HP and Rackspace and so on, you would probably see load balancing as a key feature. The idea here is, we talked about this earlier, you would basically be creating servers accessible from outside of your cloud and load balancing incoming traffic to your to a pool of pre-allocated VMs. That's just briefly about the different type of service plugins or services. Next slide. We talked about how we'd want to connect tenant networks to one another while keeping them isolated. So you could do this via either VLANs or tunneling. Tunneling would be either GRE or VXLAN. So this is actually one of the core ideas in Neutron. This is one of the most important things in Neutron. And I didn't want to kind of repeat myself because I already did a talk about this. So you're getting a bonus homework. So the talk itself via video is available at the URL on the slide. There's also the slides themselves, as well as a series of blog posts. So you can really learn about this stuff whichever way you want, via a video talk or just read at your own pace on the blog. Of course, I'm also available after this talk whenever.